Okay, maybe this is better. Excuse me for the delay, but I evaluated wrongly the time and the formulas were very large, so they did not fit well into the screen. You will see probably in the last part there will be some. So what we decided that the last part of my talk, as I said last time, will be dedicated to the central limit theorems, okay? And so the first thing I want to do is to complete the proof that I gave of the functional central limit theorem. If you remember, we only, in the lecture number 7, that in which we discussed, introduced the central limit theorems, we only proved what is probably the most important new step which is added in the functional central limit theorem with respect to the standard central limit theory, namely the emergence of the delta correlation, which is characteristic of any kind of white noise. Okay? So now we will give for granted what we did in the previous lecture. That is the lemma which establishes the existence of the limit covariance. And we show how the other correlations are taken care of. These functional central limit theorems are interesting because that will be a way for you to understand the various roles that different things play in central limit theory. And these things are, first, non-commutativity versus commutativity. Second, continuous variable versus discrete variable. You will see that they will appear two types of integrals. One integral is with respect to the continuous variable, and another is the expectation. The other integral is the expectation, which corresponds to, in the classical case, to integral over the probability space. Okay? And moreover, the non-commutativity will create the big difference between the non-crossing part of a pair partition and the totally crossing part. So the real non-commutativity enters in the totally crossing part. So let me recall the notations that we introduced in the previous lectures. D is the set of labels. You should think of the non-commutative analog of a vector-valued random variable, and D typically is from 1 to D, small d, the natural integer, is the set of components of the random variable. 0 stays for the indices of those random variables which are self-adjoint, and the set of all random variables by assumption is self-adjoint because we want that it generates a star algebra, okay? So the set of generators is always self-adjoint, and therefore if we take away the self-adjoint generators, we will have one part which is a set of generators and their adjoint, okay? Then we fix the Schwarz space as a test function space. This is a kind of exercise that you might do to verify that the test function space is not, the choice of test function space is not essential. You can replace it by Schwarz or even by step function, and you have to change correspondingly a little bit the main theorems, but not fundamental. The ideas are the same. So, then we introduce the notation, this index J or S, sometimes we use S, sometimes we use J, means that if either, because you remember that the annihilator is antilinear in the test function, because it must be the adjoint of the creator. Therefore, we put the index for this index set D plus union D0, where the dependence of the test function is a complex linear. We put F. And we put F bar when the dependence on the test function is antilinear. Remember that V is the index set, so typically V is stand like vertices, because these theorems will be applied to graphs. And in classical probability, the index set is typically the integers. And then we have a finite subset of V. Then we, remember this will be the last notation we introduce, I recall from the previous lecture, we introduce a family of subset of V, and typically in the standard central limit theorem, these are the interval from n plus 1 or n minus 1 to n. So that justifies the generalization that they have all Lebesgue measure 1, and they have all bounded diameters. So you can take unbounded set of measure 1, of course. And so we want that they have a bounded diameter in the because we will use it for continuity. Then the union, we don't require that it is RD, but we require that it is a cone in RD. Because typically the central limit theorems, for example, originally they were proved on the half line. The Wiener process typically starts at the 0. But in physics, we need the translation invariance when you want to deal with quantum fields. So in order to cover all the applications, we take a cone for the index set. And of course, this IN absorb bounded set means that every bounded set is contained in a finite union of this bounded IN. So, what is the intuition behind the transition from central limit theorem and functional central limit theorem? Roughly speaking, the transition is that you go from a single generator to functions which have valued in the generators. Since the generators are a discrete set, we can always separate the dependence on T over n from the dependence of the generator. So F is a scalar, is a complex number typically, but B and J is an element of the algebra over which, so the algebra expectation will be on this, and the integral will be on this. Of course, one could take a more general point of view and consider functions with values in the algebra. However, in my opinion, it's more convenient to keep this separation of the roles because it will give you more insight. It will show you what is governed by the algebraic probability space expectation and what is governed by the integral. Typically, the delta function will be governed by the integral and the probability expectation by govern the Bn. So the statement of the theorem that we want to prove today is the following. We have a family of Bn which satisfies the conditions of the standard central limit theorem. So uniform boundedness of the mixed moments. Uniform means with respect to the index n. Of course, typically J can be finite. Typically J is a finite set. D is a finite set. But the D is finite is not so fundamental because we take Sk is a function with value in T. So the only important point is that the values of S are finite. The range of S is finite. So we want to study the limit of these sums. And remember that this sum now depends only on f. So essentially, you replace the standard central limit is only Bn, and you have now this integral. Okay? Now, what is the philosophy of the proof? Philosophy of the proof is this. Since we know that this Bn satisfies the central limit theorem, this is essentially a scalar that multiplies the Bn. So you understand, and you can easily check, I will not redo all the steps because we already did. You can check that the products of the even moments will go to 0. This, when I have k even, will go to 0 because the integral will go out of the expectation value, En, and then I apply the same argument that I applied in the central limit theorem. You remember that what causes the convergence to 0 is the argument in the Forwaldelfes lemma, which is really the basic point both of classical and quantum. I think it is a very, very universal combinatorial argument which shows you the basic idea of central limit theory, namely the end of Gaussianity, namely the survival of only pair partitions. Okay? So we reduce to the case in which k is an even number, and from now on, remember the F are Schwarz, T is the Schwarz space. So from now on, T will be, K will be 2P. So this P that you see here is K divided by 2. And if you remember the central limit theorem, you have a situation which up to here is identical, and you see that the new point is given by the emergence of these integrals. So, what is the point? We have said the odd moment go to 0. Only even moments survive, but among the even moment, only the pair partitions survive. So, for each index here, L, there is a corresponding index. Okay, at the moment, not yet. At the moment, not yet. I will. Okay. Okay, here. For each index L, there is a corresponding index R. This is, you see, L1, R1, LP, RP. I can put together this is the statement of the theorem. This is the statement of the theorem. I want to say that. The first, from the previous theorem that we proved, we have that only these pair partitions survive. Look that now we have a single integral inside each of them. We want to prove this. So the theorem, I rephrase because I am sorry, I think there has been not. So the theorem will say that this limit will exist. For k, the k odd will be identically 0. For k even and equal to pi, this limit will exist if and only if this other limit will exist. In which now how can I disappear? I want to disappear this. How? I don't understand. Okay. It doesn't. I'm sorry, but I'm not able to let this label disappear. It disappears only if I press, but then it reappears. Okay. So, what I am saying here is that we are assuming that the limit covariant exists, and it is controlled by what we did last time, and the existence of the limit is reduced to the existence of the limit only for the totally entangled part of the pair partition. I don't remember if you have in mind what is the distinction between non-crossing and totally entangled part. In the case of the standard case that explains this difference is when you have a partition like this. For example, if you have this part and then this part is the pair partition, you see, then the totally crossing, the non-crossing part will be only this one. And using the strict singleton condition, under expectation sign, you bring it out, okay? So what remains is only the totally crossing part, which is now this one. And you cannot use a singleton because those related by the pair are the same index. So you cannot use a singleton condition to put them out. Okay? So in this formula, the formulas will be rather complicated, but this is a matter of life. In this formula that you see here, I am only considering this part, the totally crossing part, because the other part we already took care last time. We will see in the proof how to do, why this will be. So the limit exists if and only if the totally entangled part exists. And so when you understand now that the non-commutativity is driven by the expectation in the algebraic probability space. Okay? While the delta correlation is testified by this, how to say, the preliminary of the delta correlation. At the moment there is not yet delta correlation. Okay. So I will call this the totally entangled part, I call E infinity, and it will depend on the totally entangled part of the partition and of course on the test functions. Totally crossing, I sometimes call entangled instead of crossing. Okay. And if this condition is satisfied, so if the totally crossing part, the limit of totally crossing part exists, then you see that the limit of the crossing part is given by the product of the two randomness. that you can rewrite in this product here. You see that C is the limit covariance. So C essentially, if you make the assumption that, simplifying assumption, that for every sigma and every S and S prime, you have that this doesn't depend on sigma. So typically stationarity, translation invariance, for example, in lattices. And for simplicity, we do not have the dependence in N also. So we have a dependence only in S and S prime here. You see, then this product here is, you can write in a more intuitive way as expectation of a scalar product of the part which depends on T times B. So the F, this I want to keep the same index, L second J, and SL second J times B S L second J and F of the R right right and S. Okay. So you see, this is what I said before. Here you have the integral with respect to time. This is in L2 of U. And you remember that U is a subset of RD, a cone in RD. For example, the positive part of RD. So, and this is the expectation, probabilistic expectation. And now I want to try to give you the basic intuition of this proof. So this formula, in this formula, you are summing over all possible partitions which have two components. And I use this notation. The non-crossing partition as the index with the double strike, and the crossing partition with a single strike, the totally crossing part of the partition, okay? So you understand that this is a kind of partial Gaussianity. The Gaussianity has to do with the, and this is a Gaussianity which is, however, not yet disentangled. This is, if you remember, the possibility to disentangle this depends on the so-called entangled ergodic theorem. Entangled ergodic theorem is a challenge for analysts because since many years now, it is 17 years that it was first introduced, it has been proved only in for very special types of operators. There is no analog of the very, very general result that there is for the non-entangled ergodic theorem. Okay, so let me go to explain what is the basic idea of the proof. The basic idea is just this, what I already underlined, that in the transition from usual central limit to functional central limit, you separate an algebra part and the t-dependent part. The t-dependent is very similar to this. And in the next lecture, I want to show a bridge, since we decided not to give lectures on stochastic limit, but I want to show that this is exactly the type of scaling that you find in the stochastic limit, which stochastic limit is also in a stochastic limit in the particular case when you only consider a reduced evolution is called Van Hove limit, because Van Hove introduced this scaling. In total, it took it from Friedrichs, but it was totally independent on any central limit here. I hope I will have, maybe next time I will tell you the story of how this scaling was rediscovered in physics. In probability it was familiar, but in physics essentially it was discovered because Friedrichs noted something that we proved in our second or third lecture, namely that the square root of n is the only normalization that will lead to a non-trivial result. In the Friedrich case, it was the intensity in a certain limit that I don't discuss now. So now the first thing that we have to prove is that when we do this transition, the conditions which assure the applicability of central limit theorem, the standard central limit theorem, non-functional, are satisfied. And one of the most important was the uniform boundedness of the moments. And uniform boundedness of the moments comes from the assumptions on the functions f. Because, you see, when you take the expectation of these sums, you end up with the expectation, the moments will be products, these are the dots, because you have k products of this form. Now, the integrals behave like scalars, so they go away from the expectation value. The expectation value is the standard one for algebraic probability space, and by assumption, this is uniformly bounded. So we only have to prove the uniform boundedness of this. And the point is that there is a T over n, and here there is sigma. The uniformity is in respect to the index sigma. So, essentially you have to prove that this product of k integrals is uniformly bounded in sigma. And this follows because the f are uniformly bounded and the sigma have measure 1. The I sigma have all measure 1. Okay? So this is the uniform boundedness of the moments. From this we deduce that all the odd moments are 0, and in the case of an even moment, only pair partitions survive. This comes from the non-functional central limit theorem. So now we are reduced to a product of even integrals of this form. Again, we separate the algebraic part from the t part, and we write such an expectation value. The sum will be, for the moment, always the same. The sum will be over all pair partitions, but now we have separated algebraic and the integral part. Okay? Now, for each limit, now, of course, we have to sum over all pair partitions. But since P, remember, 2P is equal to K. So P is a fixed number. This limit will exist if and only if the limit for each pair partition will exist, or at least for each pair partition will exist. And therefore, we now will prove that the limit exists for each pair partition if and only if the totally crossing part of the limit will exist. Okay? So now I will not drop the sum over all partitions, and I will take only those sigma whose associated pair partition will be pi. I fix pi to every sigma. Remember, sigma is a function from sigma is a function from 1 to pi to p into the set n, and n will go to v, and the partition associated to sigma. Sigma is a pair partition, so the range of sigma is some set sigma bar 1, sigma bar p, and for each j in 1 to p, the pair is sigma minus 1 of sigma bar j is what we call the left index of the pair partition and the right index of the pair partition. Okay? This is our notation. So when you see left and right, they refer to this. Okay? So I now separate, and I separate also the non-crossing part and totally crossing part as in the figure on the blackboard. Why? Because here I use in an essential way this. If you remember the difference between singleton and strict singleton condition. Here we use strict singleton. So we can bring out of expectation value all pairs which are in the non-crossing components because of singleton condition. See, for example, if I have a pair which is not like exactly like this, but like this, you see, then I first I begin to take away the most inner ones, and then I can take away the outer ones. Okay? When you do this in more complicated, for example, I mentioned you in quantum electrodynamics, when you every time you take away one inner, some factor arises. Here we are in a very simple situation. No factor arises, just a singleton. Okay? So, when you take away all the non-crossing part, you have this product here. This product it contains all the pairs which are non-crossing. And I have brought with the iterated procedure that I have told you. What remains is the totally entangled part. But now I am considering only the non-crossing part. This is only the non-crossing part. So for each, as you see here, I have a double integral. The unification of the two will come from the lemma that we proved in the previous lecture about the covariance. Here we have still a double integral, so not white noise but colored noise. So this is the part of the non-crossing partition. And this is the part that comes from the totally crossing partition. You see, the algebraic part of totally crossing, I put Li different from Lj. This is implicit in the definition. This is how to say, already in the definition of non-crossing pair partition. But I emphasize this to remember to you that there is this kind of estimate that you need to obtain from such sums the entangled ergodic theorem. You remember? The idea is that if I add the terms that are missing here to obtain the totally to split this sum into separate ergodic sums are the terms on the diagonal. but since there is a diagonal, these terms will be of a power strictly less than the cardinality of n to the power PTC. PTC is the number of totally crossing partitions in the given partition pi. So we are now at a fixed pair partition. And it has a certain number of non-crossing, and the number of crossing, the total number of crossing pairs is exactly what we call P of totally crossing, TC. So, and then we have all these products. As you see, they are distinguished here. Here, okay. Remember that the prime apex is reserved for the totally crossing component, and the double prime for the non-crossing component. So, if we have the non-crossing component, it is like this. And so, the non-crossing component, you see, here I have P and C pairs. And the indices of this sum is P and C. With this argument of the estimate to pass from this sum to the totally entangled sum, I will do without, because we already commented this passage. We did the estimate in the proof of the standard central limit theorem. So I will go from the sum with this condition to the free sum without this condition. Once I have the free sum, I will bring the sum of inside each index. And the factor 1 over cardinality of m, I will bring in the integration. Okay? So here I have this product. I am using, remember, the stationarity assumption, the fact that this doesn't depend. Maybe here I am using this notation. I put this B0, where 0 is an arbitrary point of V, for example. In many lattices, for example, it can be the origin. Okay, so this is 0 in this notation. I am using stationarity of the covariance, so the covariance doesn't depend on sigma, and I can bring it out, and the sum over sigma now will take care only of these functions. The sum over sigma take care only of the t part, because of the stationarity assumption and the non-crossing assumption. Okay? So I have this part here. Now, as I said, I have a split. I have one factor 1 over cardinality of n for each of the P and C pairs. And so I bring each factor under the corresponding integration variable. And now I use that. Here I replace the double integral by the this is not yet. This I simply change variable. Now I change variable, and I reduce the double integral to this form. The epsilon n here is due to what I said before, the transition from the indices with this restriction to the indices without this restriction. So I obtain now this. You see now the sum is over here, over all possible indices, and the indices appear now, sigma, only on this double integral. So I cannot yet use the additivity of the integral over the volume, because I have two integrals. But if you remember the fundamental lemma of the covariance, about the covariance, this was the delta function approximation. That if I have this sum and this scaling, this is the scaling corresponding to central limit theorem for continuous variable. If you have this, then we proved the last time in the previous lecture that this sum converges to the scalar product in L2 of U. Observe, this can be infinite sum. However, the functions have compact support. So this sum for each given pair of functions is reduced to a finite sum. So it makes sense. Okay? This was proved in the previous lecture for the covariance. And so we have the limit of the covariance because it's simply a product, a finite product. And we obtain this, and I write it in the form that I wrote there on the blackboard to give more intuition, because I guess that doing random potential, you often find such kind of things. You see, this part is, the B is the part corresponding to the randomness, omega randomness, and this corresponds to the part of fixed T. So, since the limit of the non-crossing part exists, now we have proved what has been the main statement, that the central limit of the 2p moment will exist if and only if for every totally crossing pair partition, this limit will exist. So we have to prove this. This is the new part with respect to the standard central limit theorem. And as I told you, as I told you, this the new part is exactly, as you see, here you have these indices, again with this condition. And now we use the this is, I have rewritten this rather complicated expression, but the only important point is this. You see that each of these terms will have the same sigma index. You have a double integral, but we have the same sigma index here and the same index here. What can change are the component indices, and they will correspond to the pair partitions. Okay? So this is what we want to prove. Now, so now what is the point? I want to explain. This is something that we did. We will apply the estimate that we did in the previous lecture. We want to show that when the cardinality of the finite set n is very large, the difference and this is the root of the delta function. Okay? This difference will be small. Okay? That will be the difference of the double integral with respect to the single integral, which is, roughly speaking, replacing the double integral by a double integral with a delta kernel. Okay? So, we here have a product, and so we replace the double integral by the single integral, and we have to subtract the difference. So there will be one term which contains only the diagonal part, and then there will be one term which at least one delta. And our idea is that our estimate of this delta will guarantee that all the terms which contain at least one delta will be very small in the infinite volume limit. Okay? So, we now have all this product. Now we expanded the product, so we separate the delta from the other terms, and we want to prove that the limit, that essentially I can neglect all the delta here, and I can restrict to this limit of the diagonal part. The limit will be now, you see, now the expression, I will have to sum over all this sigma, and the expression will be like this. And remember, we are now in the totally crossing partitions. So we cannot simplify further. This is where non-commutativity enters. Okay. So now now I want to do the estimate of the part which will contain at least one sigma. You see? At least one sigma. This set F is the set. When I expand the product, I will have a sum over all finite set. And the finite set corresponds to the indices of the delta, where some delta appears. So this product contains the delta factors. And the important point is that this product has at least one factor. So how to estimate this proper? So the point is that this F is a proper subset of the set of totally crossing partitions. Here we now use the boundedness of the moment to say that this term is bounded because our assumption, this is only the algebraic probability space. We have to control only the integrals of the t part. So this is uniformly bounded by this M that you see here. M is the uniform bound of the norm of the modulus of these objects. So we remain only with these products of integral and the corresponding sigma. Now, so this product again, we have the product of integral and the corresponding sigma. Now, what we do? We have here the normalization factor, which is the power of all totally crossing pairs. So, of these totally crossing pairs, there will be F and the totally crossing part minus F. Those which are in F, I bring 1 over cardinality of n into this integral, this normalization, and the other one I will bring to here. So, here you see, I separate and I have 1 over cardinality of n for each index that I have to sum. now, again, since this sum, now what I do? You see, the sum here, this is the f, the indices f correspond to the diagonal part. So in the indices f, I can use the additivity of the integral over the domain of integration. And the sum here becomes the integral over the union. Okay? The integral over the union, and I bring the factor 1 over n into the integrating the differential, integrating variable. So I obtain now this quantity, but now I use that u is a cone. You see where the assumption enters. Here I am using that u is a cone. I have summed and I have reproduced u. Now I change variable, it comes this. But this is equal to u by assumption. For example, the half line. If you multiply the half line by a positive constant, you get again the half line. Okay? And therefore, this is equal to u. And therefore, you see, this is simply a scalar product of 2L, because these are very good functions with compact support, much more than L1, this product of functions. Okay? So, now, it remains to control the part which contains some delta, so which contains some double integral. But for each part which contains a delta, we use the estimate that we did last time. So we want to estimate how much is 1 over n of the difference of the double integral with respect to the single integral. And we estimated in the lemma last time that this is less or equal than epsilon times this divided by the n. This was the fundamental lemma for the covariance. Okay. So the estimate for the covariance gives this for each factor delta of LH. The delta is the difference of double integral from single integral. And so, when I sum over all the sigma of the delta, I now can use, because I have the inequality, can use the additivity of the domain. And the sum over all this integral over I sigma will be the integral over the union of the I sigma, which is again u over n, because I have changed the variable. But u over n is equal to n, so this quantity is simply the L2 norm. And here I have epsilon, which is arbitrary. Okay? So, what is, I just want to conclude with the corollary. We have proved that the limit exists. I want to say that if there is a stronger stationarity condition, this stationarity condition takes care only of the covariance. But there is a general form, a general assumption that will include all known central limit theorems of this form. The general assumption is this, is that the generalization of this to arbitrary pair partition, totally crossing. So if I have a totally crossing pair partition, E of B S L1 of sigma L1, and then it will be something, and there will be the corresponding right of the pair partitions, S R1, SR1, and here sigma R1. But remember that these sigma are equal, so I can write instead of R1, L1, because they are equal, pair partition on the sigma. And so on for the other ones. I don't write explicitly. But there will be exactly P of these objects. And I want that this is equal to something which is not depending on just generalization of covariance condition, not depending on B, on sigma. So B0 SL1, B0 SR1, etc. How do you obtain this? I will show you in the concrete central limit theorem. Here independence plays fundamental role. Because independence will split this sum in a sum that can be very big and very complicated. But it will be, whatever it is, it will be a sum of products of pair partitions. So you are reduced to this, using independence. Either independence or commutation relation is some form. We have already singleton independence. So we will, if you remember, we distinguished algebraic disentangling condition and statistical disentangling condition. In both cases, these conditions are satisfied. So this is the most general condition that allows, guarantees the existence, the central limit. Well, not the most general. It includes all the known cases, but of course there can be more general cases. Okay, so this is the pair partition stationary condition. Is what I called, just I described on the black hole. If this condition is satisfied, then this limit exists. We know that this limit exists. And it will be equal to, now we are speaking of all the momenta. For each fixed pair partition, we are summing over all possible pair partition. We have the non-crossing part, the crossing part in which the entangled part is taken care by the stationarity condition, and here you have product of delta function, product of scalar products for single pairs. You see? So this is typically of the Gaussian white noise, the product. So the non-Gaussianity will be essentially due to the non-commutativity. Okay? The non-classical Gaussianity. And now we will begin to discuss the Gaussian form, the various type of Gaussianities the next time. Well, for the next time, before we go, there is one possibility. If you want to see something similar to the stochastic limit, I can devote still one talk to functional central limit theorem, in which in the stochastic limit, when you study the term-by-term limit of solution of differential equation. When you solve the differential equation by iterated series, you have so-called pyramidal intervals. So dt1, and then integral 0, t2, t1, dt2, and so on, you see? So you integrate over the simplex, t greater or equal than t1, greater or equal than t2, etc., greater or equal than 0. The standard simplex, delta t. Okay? The analog of this will be a sum from, say, 0 to n, sum from, this will be n1, and the sum n2 from 0 to n1, etc. Okay? So you discretize the standard simplex. So if you want to see this kind of central limit theorem on simplex, it is interesting because some new features arise. Is not a standard, how to say, variant. There are some new qualitative features. which is what we call time consecutive principle. So this is maybe non-trivial. I don't know what you prefer to do, to see some truly concrete non-commutative usual ergodic theorem, or you want to see also this one? I don't know.
Yeah, you take one lecture for this.
One. Okay? Okay.